Good day to you. This is Anagalactic bringing you another science presentation. Don't want to scare you with that inset, although we're going to take a glance at it in a moment. This is a supplemental presentation where I intend to further elucidate our breakthrough discoveries made in the study of the strong force. The strong force, of course, is at one of the cutting edges of science right now. Everybody would love to understand the strong force. The strong force is a centripetal force. There are only two classes of forces when they're divided this way, when they're classified this way. This is an important part of science, is to be able to do this, but it's somewhat fluid. How would you define a force? Well, you could write books and actually whole libraries talking about what is the definition of force to its fullest explication. But if you're going to the opposite end of the spectrum, which science definitely wants to do in a cycle, is to summarize, then what is a force? It's one of two. That is the ultimate simplifier. That is the integral or infinitesimal of Occam's razor. If you're trying to get at something with induction, you're going to have to classify what you're even talking about. Otherwise, you can't define what you're talking about. It turns out that science is still having a problem with that in its definition of force. That is a remarkable thing to be able to say in context, because just looking at this little inset here, that light blue line that is coming in from the right you can think of, then dipping and then skyrocketing off of the top of the graph, that is force. That blue line is force. But you understand now from what we've just axiomatically declared, my statement is utterly incomplete. That can't be a force. It can only be a relationship between two forces, if there is such a thing. And that's where geometry comes in. So our classification is not quite complete, even when we declare, as can be stated and proved, there are only two forces. That can be proved. Well, do they have names? Yes, they do. One of them is gravity. That's one of the two forces that operates at macroscale. So now there's an added level of complication. Gravity is actually not a fundamental force, but it sure feels like it is when you're standing on the Earth. Everything in our lives is basically undergirded with gravity. We wouldn't be on Earth if it weren't for the gravitational field of Earth. Well, you can extend that list. There would be no Earth if it didn't revolve on its axis. That's a spherical rotation. And there would be no ecology, no heat cycle, no nothing, if the Earth were not going around the sun. Well, why is the Earth going around the sun? It actually took quite a while in science to be absolutely certain that the Earth was going around the sun. Well, that means that the sun exerts a gravitational field. It also describes, that is, gravity describes the shape of the sun, which technically is called plasma, although there is also a footnote, as there usually is. But the sun is essentially what's called the fourth state of matter. Well, we know of solid, that's ice, liquid, that's water, and gas, that would be water vapor. Or in fact, the Earth's atmosphere itself is gas, and there's a footnote to that. But the sun is not gas. It's quite hot. Well, that ionizes the atoms, essentially. It's why it's called plasma instead of a gas. Because basically the temperature, so there's another scale that we didn't figure into our original classification of force. Force occurs at different scales. And to say that there are only two forces may still be true, but now it's contextual. Let's look at this diagram again, and if you watched the last video, or preferably the last two, although I'm not directing you to do so because I'm going to summarize it now. This is the job of a scientific presenter. You don't have to do homework. There's no homework in this class. It's voluntary. But I'm going to summarize it so if you're interested, you can get more details. In the last one or two lectures, you will definitely find out what this little curve means. This is the relationship between two protons at quantum interactive level. Now, most of the problems in quantum mechanics have to do with electrons and photons. There aren't too many quantum paradoxes that are popularized that have to do with protons, because protons are a completely different kind of particle. Well, not completely. However, the proton exhibits a relationship with the electron that shows that there are two forces. And the reason we can say that is because the electron shows a relationship with a proton that is directly proportional to the proton's action on the electron. But they are certainly not the same. They're hierarchical. And that can be seen in one of two ways. What's the relationship between the proton and the electron? If you state it electromagnetically, it's a charge relationship, right? That has a certain valence, opposite charges. That's a geometric statement. Plus and minus have a geometric connotation. So you could say that the proton has a centripetal force relationship with the electron because it pulls the electron in exactly as if it were exerting gravity on the electron. Now the electron would then be expected to crash into the center of the proton. And indeed, in a linear reduction, it can be shown that as that electron with its minus charge accelerates toward the proton and goes faster and faster until finally what is mathematically describable in one of several possible outcomes, but the linear reduction would be total annihilation of both particles into a null. Because if it's pure plus at the center and pure minus, and we know the charge relationship forces the electron to accelerate towards the proton, this is not mutual. The proton just sits there. That's called an inertial frame of reference. That is shown on this diagram as the zero mark on the extreme left. At the center of the vertical line is that zero. So this graph is divided by a horizontal line which represents space. The question, and this was asked by a commentator, even after I explained it, so I obviously did not explain it very well, certainly not well enough for him, and I answered him. He hasn't replied yet, but it's a very natural question to ask. Is the vertical line the second spatial dimension? No. It's a force dimension, which is non-spatial, obviously, because it's force. And it's labeled that way, so the question was a little bit... But I thought it was a good question anyway. Well, all questions are good questions if the professor thinks about it long enough, because it's the professor's job to answer the question, why is this person asking this question when there's an obvious answer? And it's the professor's job to do some psychoanalysis if necessary and figure out why the student did not get what the professor said. Well, there's this is an extremely common question. In fact, I think everybody asks this question. It's just that we become convinced that we know the answer. Well, not everybody is as easily convinced. That can be a positive sign. So you don't ever want to say or even think, if you're presenting as I am, that question is dumb. You're going to be wrong every time. No, that question is not dumb. What you could say if you were mean is it sounds dumb. You're not allowed. I'm not here to say that someone's dumb. The person came in dumb and wants to be intelligent. So you don't say to that person, well, you're dumb. It's like someone coming in for treatment from a doctor, and the doctor just rants at him and says, why the hell did you let this happen to yourself? That's not why the person came in. You know, maybe there's a little advice at the end, but it's friendly. Like you might want to read the label on the bottles next time or something like that. But, you know, the person came in to get progress. They're coming to you for help, not criticism. So the natural tendency, I would say, speaking for myself, well, I'm dumb too, because when I first saw this graph, for the longest time I kept looking at the blue line as if that were the flight of one of the particles. More than once in a row, I just didn't really pay much attention. I was trying to figure it out just by looking at it. And I read, you know, it's force going vertically, but nah, it's space. Because in a 2D diagram, it should be all spatial, right? If you draw a circle on a plane, well, what is the up and down different from left and right? No, it's spatial. So this looks like it's a spatial curve. Well, it's not. It's a hybrid, though. The horizontal line represents space. So space goes like this in the diagram. It doesn't go up and down. It just goes sideways. That's called the linearization of a space distance. It's redundant to say so because the very basis of Euclidean geometry is the shortest distance between 2 points is a straight line. That's the basis of science. If you have 2 points, the shortest distance is a straight line, yes. It's virtually the definition of a straight line in that sense. So why is this line curved? Well, it's curving out of the spatial dimension. In fact, it actually never touches the spatial dimension, except at one point, which we talked about, but it's my job to summarize, so I'm going to summarize that now. By the way, that's not a very flattering image, so I'm just going to let this go for a second. That blue line, pardon me, that blue line... I'm dyslexic, so... skyrockets. What does that mean that it's going up so precipitously? It means that the force relationship is shifting. All right, I think you got that. That blue line has 2 curves on it, correct? Let's take a quick look at that again. There's a curve on the right of the dip, and there's a tighter curve on the left, and reverse right and left. If you start your analysis of this graph by looking at the low point, what does that mean? Where it dips and then curves back up, going right to left. First of all, what does it mean that it's coming in that way and dipping? That's increasing repulsive force. And then it reaches a maximum repulsive force at the bottom of the curve. And then it reverses its direction. but not reverses in the sense of plus and minus. It's not reversing polarity 180 degrees. This graph proves that. Now, it depends on the metric of the graph. This is a 2D graph, but it's not 2D planar. It's 2D composite, such that one of the axes, which is the 0 line going horizontally down the middle, that represents space. And that is the only object in this diagram that represents space. It's entirely on that horizontal line. There is no space around it. In other words, it's a reduced space. It's called a linearization of space. And the linearization of space is very easy to define. It's a straight line from point to point. From point to point. Now, here comes the proton, and we're going to say that it has velocity. We're going to say that the velocity is 10. But now we need to define what that velocity will imply in terms of it, the proton doing what is it doing? The proton has been fired from a gun. Just think of it that way. So it has an artificial velocity. And now it's been fired at another proton. You may already know, and I'm pretty sure you do, or you're aware, that a hadron collider does exactly that. It fires a proton directly at another proton to see what will happen. What do you say will happen? Newton had an opinion. Leibniz had an opinion. Boschkovich, Einstein, Dirac had an opinion. What happens when two particles, in this case protons, because you know there are two particles, that's extremely important. The electron must be considered a particle. But I'll show you, you also need to know the difference, and that's very rarely discussed, is the difference in structure of a proton and an electron. So we have two chapters that we need to deal with. This diagram here is only talking about one of those particles, the proton, the one I call the spatial particle, because it creates a position in space. By the way, the electron does not. We can positionalize it, and that's called locality, but it has no clear center to the same degree that a proton definitely has a definable center. You can see it on this graph as the 0, 0. The 0, 0 is at the far left of the central horizontal line. It ends at the center of a proton. That can only be a proton. There is no center to anything in an electron. Now remember, there is also a specific force relationship between the electron and the proton, and we're getting to that. But this is the simplest of all the relationships. But in the simplest binding, since it is linear, in fact it's countable, you can have just one proton. We now know that space is conjugate with something else that's non-spatial. So far, we've been able to identify that non-spatial domain, which is not space, but it's real. We call it time, and that has driven men to psychosis. because time is not a domain. Space is, but time is not. And yet Albert Einstein proved that there is an orthogonal relationship between linear space and time, which results in curvature. And that curvature is called the curvature of space-time. There is such a thing as a curvature of space, and we can see it in this diagram. We're getting there. But is there a curvature to time? No. No, there's not. But you can pretend that there is. And the reason you can pretend that space-time itself is curved is because you can pretend that time is curved because space is curved, but it's not represented in our system as curved. Space is never curved in the linear system. Space is always 3D, always 3D, always 3 lines, always 3 lines, always 3 lines. A sphere doesn't know what you're talking about when you say straight line. So the question is space linear? No. Einstein proved that space is not linear. But the way he proved that space is spherical, which it is, space is spherical. The way he proved that it's spherical is by taking cubically linearized space and discovering the 4th linear component, which in the derivative system, which that is, 3D is derivative of sphericity, 4D is derivative of spacetime. This graph is not lying. That curved line is a continuous line. That means it's dequantized. It's showing an absolute relationship between 2 fundamental components of reality. This is the intersection of visible reality with invisible reality. Why is this other reality invisible? It's orthogonal to perceptual human space. We cannot see it until you understand quantum entanglement and quantum superposition as being the same thing. And once you see that quantum entanglement and quantum superposition are the same thing, you will understand anti-gravity, because there is an anti-gravity component that I discovered, and it's on this graph. That line shooting up on the extreme left of the blue line curve, where it shoots up to infinity. Do you know which infinity it's shooting into? It's shooting into the imaginary infinity. How do you solve that? It's by realizing that the spatial infinity going perpendicular to this infinity, those make space energy. So the energy domain is perpendicular to space. That's why the electron behaves so strangely. But most importantly, that absolutely describes the flight of the photon and unifies Einstein's 2 insights, which he basically published at the same time, that the photon is a particle and the photon is not a particle. He proved both, and now we need to see why that's a paradox. It's because you're not seeing where time actually is. Time is not on this diagram, but time is somewhere on this vertical asymptote. There is no time on the horizontal. That's space. And there's no such thing as space-time. This diagram proves there's no such thing as space-time. What there is space that's orthogonal with a spheric energy system. I discovered the geometry of that system. And I'll show that to you in the next presentation, and that's 50 minutes. Stay tuned and keep looking up at night. The full moon is waning. This is June 26th, the Wednesday from Chico, California, bringing you the secrets of the universe. Stay tuned, and as always, thank you for tuning in. Thank you very much, and I hope to see you next. I'm looking for the off button because I'm using new software. Stop recording. See you next time.